We have been talking about enzymes. Enzymes are proteins that catalyze chemical reactions in the cell without being used up or changed in any way. They go in the same and they come out the same. And they work by lowering the energy of activation, the energy that's required to get things going in the first place. Down here we have what our energy graph would look like with an enzyme. It lowers that bump right there. That is much lower than this bump here without an enzyme. Right, and they do that. Well, how do they do that? They don't just wave their magic wand and say, poof, you have a lower energy of activation. They do that by binding to substrates at their active site. We talked about this last time, but just a little review here. That enzymes have an active site. Let's draw that again. Our enzyme before the substrate's bound to it looked like this here, and we call this area here the active site. You already have that in your notes, and I made it obvious here that these reactants, substance A and substance B over here, would bind to the active site. And it spits them out, and it goes back to the active site, goes back to looking the way that it did before. Pardon me, gotta drink a little bit here. All right. Now over here, if you take a look on the right side of your screen here, I talked about how what if something happens to the shape of the active site and it gets all messed up, and the active site, instead of looking like it's going to bind to a triangle and a ball, looks like something that's not going to bind to a little triangle and a little ball-shaped thing. All right, that means that this enzyme wouldn't work to catalyze this reaction anymore. The shape of the active site is so important. Now, do you remember back, or shall we think back to when we were talking about how proteins get their shape? And there were 4 levels of protein shape. The first level was the order and number of amino acids, and at the second level they got all these alpha helices or maybe beta pleated sheets. And then at the third level, all those beta pleated sheets and alpha helices, would fold over onto each other and form, say, a globular enzyme, and maybe that shape led to something that looked like it would bind to a triangle and a ball, our active site up here. This is our active site right there. Okay, and we talked about, well, why do we even care how proteins get their shape? Why is shape so important? And we talked about how shape determines function. And we talked about how, I'm sitting here writing with this little stylus that is shaped like a pencil. It's a stick. And things that we write with, writing instruments, are generally stick-shaped. They have a shape, like a stick, that determines their function, something we can fit between our fingers and write with. The shape of our useful objects is really important. And the shape of an enzyme is really important. An enzyme with an active site that looks like this does not look like it's going to be able to bind to a little ball and a little triangle. It's not going to work. So the shape of a protein is really important. But there are things that will mess with the shape of an enzyme and with the shape of a protein in general. So, for example, every protein has what we call an optimal temperature where it works best. So, optimal temperature for an enzyme. This means the temperature at which an enzyme will work best, and it'll bind to its substrates best and be able to catalyze that reaction best. And let's say most enzymes that human cells produce and use. So for humans, This optimal temp is around 37 degrees C, which is body temperature. Yes, I know, you're like, what about 98.6? Well, that's Fahrenheit. This is science, so we're doing Celsius scale, and that is 37 degrees C is optimal. So most enzymes in your body work best at 37 degrees C. If you have a fever, your enzymes might not work so well. We can actually use this, though, to help out people. For example, you know that most of the foods you eat are not sterile, right? You order something through Instacart or however you get your groceries these days. You know your lettuce isn't sterile. I mean, good grief. How would we do that? Boil our lettuce and there it would be sterile, except that we would have boiled lettuce and that would taste gross. So, you know the food we eat isn't sterile. So we clean them to basically get any microbes off of it. You know, you wash a lot of vegetables and fruits before you eat them. But let's think to, let's say you're going to throw something on the grill. Let's say, I don't know, you're going to grill a steak. I don't eat steak very often myself, but you know when you buy that steak, it's actually got some bacteria on it because that thing is not sterile. It's been cut with knives that aren't sterile by the butcher shop, and it's wrapped in saran wrap and on, styrofoam if you buy it that way at the grocery store. You know that there are going to be microbes on your steak. I don't think I could draw a steak very well. Let's pretend like this little round thing is a steak. This looks ridiculous. Well, let's say your steak has some microbes on it. Okay, you're not going to eat a raw steak, are you? How are you going to prepare that steak for human consumption? If you said you're going to cook it, yeah, we cook food. Now, how are you going to cook this particular steak? Most people cook it on like a hot frying pan or on a broiler, or we just throw it on the grill. Okay, and the grill, the heat from the fire destroys all of the microbes that are on your steak. All right. Oops. I got rid of my steak there. Come back, steak. Okay, so we use heat to prepare it for human consumption. Maybe I do need to put those microbes back on there. Okay, so no microbes. One of the things that heat does to kill microbes is that heat messes up microbial proteins. Like, let's say that our enzyme Q that looks like this, let's say this is a bacterial enzyme. If you heat it up, like with fire, and actually usually for most microbes that are human pathogens, if we just heat it up to like 72 degrees C or higher, what happens to the bacterial proteins is that all those alpha helices and beta pleated sheets that are in there open up, and you just have one long polypeptide over here. This over here does not look like it's going to bind to a little triangle and a ball. It has lost its shape. So we say that the enzyme has been denatured. Denatured. And denatured means that it has lost its shape. We can denature bacterial proteins that are on our food by heating up our food, and the heat denatures bacterial proteins. If bacterial cells don't have functional proteins anymore, that cell is going to die, and that makes the food safe for us to eat. So we use heat to prepare our food, in part because it destroys and denatures bacterial enzymes and proteins. So heat will denature a protein. So heat can denature proteins. And we use this. Okay, oh, that was a reminder. Shoot, I put this on airplane mode, but that doesn't stop my own reminders from reminding me to do things. I will edit that out later. Okay, so heat can be used to denature proteins. Oops, there we go. Fix that. Okay, we use heat to destroy bacterial proteins that kills the bacterial cells, and makes the food safe for us to eat. So one of the reasons that it's great to cook a steak or chicken or what have you on the grill is that heat denatures bacterial proteins. It destroys the bacterial cells, right? But you don't just have to, flame the bejesus out of food to destroy bacteria. Another example of using heat to denature bacterial proteins and destroy bacterial cells to prepare our food is through the process of pasteurization. Can you think of anything that has been pasteurized? And if you said milk and other dairy products, then ding, 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 you are correct. The pasteurization process uses heat to kill not all, but most of the bacterial cells present in, for example, milk. So pasteurization uses heat for a short period of time. Like heating up milk for like 20 seconds to denature most bacterial proteins and kill most bacteria in milk, for example, not just milk, but ice cream and other dairy products. Most bacterial in milk, but let's say doesn't kill all bacteria. So pasteurized milk is not sterile. Pasteurization is not, or rather does not equal sterilization. I mean, when you buy, let's say a half gallon of milk and it's got an expiration date on it and stuff, okay, you know when you open up that milk, it's not going to last forever in the fridge. It's going to go bad eventually. That's because it has not been sterilized. Just most of the microbes that were present on the milk that, the milk picked up on its way out of the cow or goat, if you're drinking goat's milk, it picks up bacteria from the cow or the goat's skin. And so it's collected into, even if you collect it into a sterile container, a sterile bucket, let's say, there's still going to be bacteria on that milk that it picked up on its way out of the cow or the goat or sheep's milk, if you're going for sheep's milk. So we pasteurize it by heating it up for just a really short period of time to kill off most of the bacteria in the milk by denaturing just many of their proteins. But it's not sterile, and that milk is not going to last forever in the fridge. So pasteurization, it still uses heat, it still denatures bacterial proteins, but it doesn't kill all of the bacteria. To do that, we'd have to boil the milk for a time, and that really changes the texture of the milk, and people tend not to like that. For example, There are boxed milks that you can buy that have been pasteurized for a much longer period of time, and they actually have been sterilized. So that milk in a box that you buy on the shelf, I think the brand is Parmalat. It is sterilized, okay, because that's been heated up for a longer period of time. They still might use a pasteurization method, but for the most part, pasteurization doesn't sterilize your food, but it kills off most of the bacteria, which makes it last a lot longer, while it's traveling in a refrigerated truck, while it's sitting in the refrigerated section of your grocery store, while it's sitting in your fridge. But it's using heat to denature proteins. Okay, so we use heat to denature bacterial proteins, which will kill the bacteria and make the food better for human consumption. Can you think of any other ways that we use to preserve food and make it safe for us to eat? And here is often where somebody will say, we put things in the fridge. Yeah, we put things in the fridge, but that is still using temperature to slow down any bacterial growth. So something other than temperature to preserve food. Think hipster stuff. What's really big right now? What's really big right now for preserving food is using fermentation or No, I don't want to go there yet. Think pickles. Yeah, that's kind of a hipster thing to make pickles. Think about how you make pickles. You add a bunch of acid and salt to something, right? Salt basically dehydrates cells. So we know how that works from our hypertonic thing going on. But we can also use pH to denature proteins. And this will also preserve food for us. So for example, if you've ever heard of something called ceviche, I think that's how you spell it, ceviche. It's a common food in a lot of Central American cuisines. Some Mexican cuisines have this, Puerto Rican cuisines have something like this. And you basically take fish, and it's usually a white fleshy fish, or a lot of the time they will use shrimp. Shrimp is used to that. And you add lime juice, which is wicked acidic, or other vinegary things. Vinegary, I can't spell the word vinegar right now. Vinegary solutions. All right, so you could use lemon juice. Lime juice is a really big one. And you basically pour your lime juice, your really acidic lime juice, over your fish or over your shrimp, and you let it, really sink in. And what it does is, let's say this is a bacterial enzyme right here. You add acid to it, which is low pH, and it opens up that enzyme into just a polypeptide chain, and it denatures the enzyme. I'm not sure where you are in lab right now with your virtual labs, because I don't teach Bio101 labs this semester, so I'm not sure exactly where you are, but you are probably doing an enzyme lab where you do a little simulation of how well an enzyme works at different pHs. Most of them don't work at a very low pH or a very high pH. So messing with the pH of a cell will denature enzymes. Another thing, another example of this in human cells, let's talk about that. I think it's next week, April the 20th, that was going to be the Boston Marathon, okay, which has obviously been canceled. All these events are canceled right now. But during the Boston Marathon, I have a friend who has worked the Boston Marathon for a number of years, and she worked at mile 17. And they saw a lot of people at mile 17 with a particular issue. And that particular issue was a muscle cramp, okay, out of 26 point however many miles a marathon is. At mile 17, people are sometimes getting a little tired. Muscle cramps are a result of lactic acid buildup on your muscles. That's a muscle cramp. And if you've ever had a muscle cramp, they hurt a lot. And it makes your muscle, like let's say it's on your hamstring, you have a muscle cramp in your hamstring, it makes your hamstring like hard as a rock. You cannot run very far with a muscle cramp on your hamstring, and that's because a whole lot of lactic acid builds up. Okay, your muscles are protein, muscle protein. The lactic acid denatures your muscle proteins very slightly. And when those muscles lose their shape, I mean, most muscle fibers are very long, fibrous muscles like that. If they lose their shape and feel like you have a little knot in your muscle, man, that's going to hurt. That muscle cramp will hurt. Now, the good news about lactic acid is that as you rehydrate yourself, this muscle protein will regain its shape. It'll recover. And it'll be nice and fibrous again. But again, you got to break up those lactic acid knots there, and usually you can do that through just some good hydration and some massage, and that is what my friend does. She is an ENT, she is a nurse and a massage therapist, so that's exactly the kind of person you would want at mile 17, especially if you had a muscle cramp. So let's see. So that is using pH to denature your enzymes and proteins. So we looked at that. There we go. All right, so far, let's get a different color here. Let's go with blue. Let's just think about what we've talked about so far with how your cells make energy, because this is the unit that we're working on. We've talked about energy and the laws of thermodynamics. Sure, we got that. We talked about endergonic and exergonic reactions. We have talked about enzymes and how they work, and they end in the word ace, and how to mess up the shape of enzymes. Next up, before we can talk about how our cells take a sugar molecule, eventually combine them with oxygen and get to CO2 plus 6H2O plus some ATP, there is one more type of chemical reaction that we need to talk about. And so what's up next are, and here's our heading right here, we're going to talk about types of reactions called I cannot spell, got right to that X first. Oxidation and reduction reactions. Oxidation and reduction reactions. Way back when I had my map of the US up here, I'm not going to scroll back to us because that's going to make our eyeballs spin around. I talked about how going from C6H12O6 plus 6O2 yielding 6 CO2 and 6 water molecules, O plus ATP, that this doesn't happen in just one reaction. It happens in a whole series of about, 20 reactions or so. Some of those reactions will be endergonic, some will be exergonic. Some of these reactions will be oxidation reactions, and some will be reduction reactions. So, what are oxidation and reduction reactions, you may ask? Here's the definition. An oxidation reaction is when something loses an electron. If a molecule loses an electron, that's an oxidation. Reduction is the opposite. If something gains an electron, one or more electrons, it's a reduction. Okay, so I want you to leave a little bit of room in your notes because we are actually going to come back and add to this, but how the heck are we going to remember what an oxidation and a reduction reaction are? I can't, it has something to do with electrons, who cares? How do I remember this? There is a little stupid way to remember how this works. And you know how sometimes people will remember something, like they'll remember a sentence by just picking out the first letter of each word, and like they use that for their password. We're going to do the same thing here, and this stupid, silly little mnemonic to remember is Leo, the lion, goes grr. Leo, the lion, goes grr. And this stands for Leo, you lose an electron. It's an oxidation. Goes grr, you gain an electron. E for electron, it's a reduction. So there you go. There you have it. Leo goes grr. If you need to remember this at any point, because trust me, I'm going to be asking you on the next exam, just remember Leo, the lion, goes grr. Sometimes people do oil rig. Oxidation is losing an electron and reduction is gaining an electron. I like Leo goes grr because it's stupider. It's sillier. Like, oh, who says it goes grr? It's like we're talking to a child here. But oil rig might work for you too. But we are going to need this room here, so I'm going to get rid of all this stuff. But remember, Leo goes grr. Lose an electron, it's an oxidation. Gain an electron, it's a reduction. Get rid of that there. If you need it back, if you need to see this or to write it down again, just go back and watch that part of the video again. Alrighty. Okay, so an oxidation is losing an electron. A reduction is gaining an electron. Let's look at an example here. So for an example, let's say I have an iron ion. Say that 12 times really fast. Iron ion. Iron ion. Iron's abbreviation on the periodic table is Fe. It stands for ferrous, ferric, like Ferris Bueller's Day Off. Iron, Fe, it's Greek. That's where it comes from, so don't worry why it's not an IR. But let's say there is an iron plus 2 ion. This iron ion, iron plus 2, can lose 1 electron. So I'm going to do it this way and show a little arrow coming out of the main arrow and show 1 electron coming out of there. So this iron plus 2 ion won't be plus 2 anymore. Can you think for a second what it's going to be if this bad boy over here loses a negatively charged particle? Is it going to be plus 2 anymore? Nope. What will it be? Plus 1? It is not going to be plus 1. It will be plus 3. It will be an iron plus 3 ion. Because this plus 2 has lost some negativity. It has lost this negatively charged electron, so it's going to become more positive. That's how that works. Is this chemical reaction here, is this an oxidation or a reduction? Let you think about that for a second. It is an oxidation because it has lost an electron, and if something loses an electron, it's an oxidation. This process of oxidation here, this iron ion becoming oxidized, this is rust. This is how rust happens. The rusting process of the iron that is in your non-stainless steel, iron that's in the steel, for example, underneath your car, it rusts. It loses electrons, and that's what rust basically is. Rust is a result of the oxidation process. So that's that is an example of that. All right. So there's something funky here, though. Like, what the heck is all this electron stuff? Like, who cares? This is a biology class. I don't care. This looks like chemistry, all this stuff about electrons. And it's true. Oxidation and reduction reactions were first described by scientists who were basically chemists. They were looking at things in test tubes or setting up battery cells. And, if you ever took a chemistry class where you had to, like, set up these battery cells and something was being oxidized and something was being reduced, like, what does this have to do with the cell? It does have something to do with the cell, but in the cell, we look at oxidation and reduction reactions a little differently. And here's why. Let's pick out a new color here. Let's go with purple. All right, in the cell. No, let's not go with that purple. Let's go with the darker purple that shows up better on your screen. But in the cell, when a molecule loses an electron, it usually also loses a proton. This is huge. And we'll talk about why in just a second. So when a molecule loses an electron, when it's oxidized, it usually also loses a proton. And, well, the reverse of that, when a molecule gains an electron, and again, this is in the cell, when a molecule in the cell gains an electron, it usually, and I'll put that in parentheses because I can think of one example where it doesn't happen, but it usually also gains a proton. Okay, in the cell, when a molecule in the cell loses an electron, it usually also loses a proton. And when a molecule in the cell gains an electron, it usually also gains a proton. Did anything sound funny to you there? Somebody is sitting at home paying close attention, and somebody's going, I don't know what the heck you're saying, Professor, but I heard you say something weird that wasn't what you wrote down. And I'll be like, oh, what's that? And you're like, okay, when a molecule loses an electron, we're up here, it usually also loses a proton. Why did you write H plus instead of this word proton? And when a molecule gains an electron, it usually also gains a proton. What is up with that? Why did you call this a proton? And I'm telling you that I have not lost my mind, but I am telling you that I know this. This is true, that, let's go back to purple, a hydrogen plus one ion is equal to a proton. So we're going to circle that and put some stars around it. I can totally use these terms interchangeably. Instead of writing out the word a proton, I can just write H plus, a hydrogen ion, right there. Less writing to do. And if you still think that I've totally lost my marbles, let me explain why after I draw this really pretty little gold star there, because this is super important. There we go. Let's think back to where hydrogen is on the periodic table. Do you remember our periodic table? Hydrogen was the very first atom on the periodic table, and its atomic number is 1. Okay, and remember, what does that atomic number 1 tell you about a hydrogen atom? And if I draw it like a circle, yes, I know atoms aren't circles. I know you know that atoms aren't circles, but I got to draw something to keep it confined in an area on notability here. Its atomic number is 1, and that means there is 1 proton in its nucleus. I'll pull this down a little bit. Back to here. Okay, the mass of a hydrogen atom is usually 1, so there's no neutrons in there. So there is 1 proton in its nucleus, and there is an electron out here. If it's a neutral atom, there's going to be 1 electron outside the nucleus. And this is it. This is all that a hydrogen atom is. It is a single proton in the nucleus and 1 electron outside the nucleus. This is why I made you learn all that stuff back then. Because we need it now. All right, but think about what happens. Let's say that this hydrogen atom is a part of some other molecule. And if it's going to be oxidized, it loses an electron. Think about what happens if it loses that electron right there. That's all that this is going to be now. Now, this is not a hydrogen atom anymore, right? It's not a hydrogen atom. It's going to be a hydrogen plus 1 ion, right? So imagine, think about it this way. Going back here, when a molecule loses an electron, it usually also loses a proton. This little proton's like, well, wait, I don't want to go anywhere without you. So if this electron here is going to some other molecule, this proton's going to go with it. So in the cell, and again, we're talking molecules in the cell, when they lose an electron, they also lose a proton. Think about what an electron plus a proton equals. An electron plus its proton here make a hydrogen atom, don't they? Oops, not an S on there, a hydrogen atom, right there. So if we scroll back here to our original definition of oxidation and reduction. Oxidation, right here, is when something loses an electron. But if something loses an electron, it also loses a hydrogen. When something loses an electron, it's also losing a proton. So what it's really losing in the cell is a hydrogen atom. So we are amending our definition of oxidation and reduction. An oxidation is when a molecule loses an electron or hydrogen atom. Likewise, when a molecule, down here, the bottom of your screen, when a molecule gains an electron, it usually also gains a proton, which we know is the same thing as a hydrogen plus 1 ion. If something gains an electron and a proton, it's really gaining a hydrogen atom. So a reduction up here. A reduction reaction is when something gains an electron or hydrogen atom, like that. Let's take a look at what this is going to mean for us in cellular respiration. C6H12O6 plus, what did we have, 6O2 yields 6 CO2 molecules plus 6 water molecules. Oop, you know what? I'm going to make this a little... no, I'm not going to do it that way. I'm going to color code here. There, how's that? Now remember way back when, in the last lecture, we connected these and I was like, okay, I am 100% sure that all of the carbons in glucose get converted to CO2. Remember when we wrote happens first? And then we connected the other two here. And we were like, it happens last. This part up here that happens first, C6H12O6, glucose, becoming CO2. Is this an oxidation or is it a reduction? Think about that for just a sec. 1 Mississippi, 2 Mississippis, 3 Mississippis. It's losing these hydrogens here, isn't it? And if we're like Leo goes grr, you lose an electron, that's an oxidation. These are losing electrons or hydrogen atoms. It's an oxidation. This is an oxidation. It loses hydrogen atoms, right? So down here, this one, O2 becoming H2O. Hey, it's gaining hydrogens, isn't it? Yeah. So a reduction, okay, Leo goes grr, you lose an electron or a hydrogen, it's an oxidation. Grr, you gain an electron or a hydrogen atom, it's a reduction. This is a reduction because it gains hydrogen atoms. Yeah. So when something is oxidized, it's not just losing electrons, it's losing hydrogen atoms. So again, an oxidation. So when something loses electrons or hydrogen atoms. A reduction reaction is when something gains one or more electrons or hydrogen atoms. Right there. Okay. So so far we have talked about endergonic and exergonic reactions, oxidation and reduction reactions, enzymes, the laws of thermodynamics. There's one more little bit that we need to talk about before we can put all of this together for how we start with glucose and end up with CO2 and water and ATP. All right, and that is a set of players called electron carriers. Electron carriers are molecules that carry electrons. Big deal. Who cares? What does this mean? You will see what this means very shortly. But there are two of them. Okay, and there is one called NAD+ is an electron carrier. Don't worry about what the heck the NAD stands for. It's like nicotinamide adenine dinucleotide. We do not need to write that out. No one does. And another one that is FAD, and it doesn't have a plus or minus charge at all. And that's like flavin adenine dinucleotide. Who cares? It's FAD. All right. So what do these things do? They actually remove hydrogen atoms from glucose and bring them to the mitochondria. So they remove hydrogen atoms from glucose and bring the hydrogen atoms to the mitochondria. Okay, you all know that the mitochondria is the powerhouse of the cell. It's got something to do with how cells make ATP, so it's no surprise that we're going to be getting into the mitochondria at some time. But what NAD+ and FAD do is they remove hydrogens from glucose, our C6H12O6 up here, and they bring those hydrogen atoms to the mitochondria. Big whoop. Let's add a little bit to this. In the mitochondria, In the mitochondria, those hydrogen atoms are going to be used to make ATP. Here we go. So let's see how this happens. Well, let's start off with FAD. It's not a very common one. We won't see it too often, but it's a little easier to think about. FAD can actually take on, I'm going to draw this arrow pretty big here, 2 electrons, and where 2 electrons go, 2 protons are going to go, so 2 protons. Now what are those 2 electrons and 2 protons going to make together? This thing won't be FAD anymore. Remember that an electron plus a proton equals a hydrogen atom, a neutral atom. And there are 2 of each here, so this is going to be FADH2. There you go. FADH2. And likewise, an NAD plus is actually the more popular one in the cell for whatever reason. It takes on 2 electrons, but only one proton. So it becomes NADH. Because of these 2 electrons, one of them is going to neutralize this +1. And then the remaining 1 electron is going to get together with the remaining proton and form a hydrogen atom, NADH. So let's look at an overview of how this all works. Okay, I'm going to write this out. I'm going to color code things a little differently, so don't wig out when you see how I'm going to draw this. 6 plus 6O2 becomes 6CO2 plus 6H2O. I'm going to color code those hydrogens here. So it's C6H12O6 plus 6O2 yields 6CO2 and 6 water molecules right there. The way this works is that, and this is just our overview thing here. NAD plus and FAD will pick up those hydrogens from glucose and become NADH and FADH2. Okay, and there are going to be a bunch of NAD. I know the numbers aren't matching up here, but they will later on. But I'm coding them this way to show you that NAD and FAD, NAD plus and FAD remove these hydrogens from glucose and they become NADH and FADH2. Then they bring those hydrogens that came from glucose, and that's why I'm putting them in yellow here, into the mitochondria. Let's color the mitochondria in orange. Remember, the mitochondria has 2 membranes, like that. So NADH and FADH2 accumulate, and a bunch of these, there'll be like 6 of these here, 5 of these there, or whatever. They'll accumulate in the mitochondria, and those hydrogens are used to make energy. So once in the mitochondria, the hydrogen atoms that came from glucose from glucose, your C6H12O6, those hydrogen atoms are used to make a crap ton of energy. Well, let's not even say the energy. Let's say ATP. And how that process happens, we will be talking about for sure. But this is an overview. And we're not even done with our overview yet. Once those okay, so all these hydrogen up here in the upper left-hand corner here, we've got C6H12O6. Those hydrogens are ripped out of glucose little by little, not all at once, little by little, and they're picked up by NAD and FAD. NAD plus and FAD become NADH and FADH2. They get inside the mitochondria, and these hydrogens make ATP there. Make ATP. And once they're done making ATP, then those hydrogens join with oxygen to become water. So let's amend this. Once in the mitochondria, the hydrogen atoms that came from glucose are used to make ATP. After ATP is made, the hydrogen atoms bind to oxygen and not make water, let's say become water. So that's our little story here, and it's pretty much summarized by all this right here. Yeah. And again, NAD and FAD over here on the left here, they don't rip all 12 of those hydrogens out at once. It happens little by little by little. And that happens through several processes. Now, these processes are called the central metabolic pathways. Dun dun dun. It happens through several processes that we call, the first step is called glycolysis. Lysis means to break something up, and glyco means carbs. So we're breaking up carbs in glycolysis. Then there's a process called the transition step. And another process, the next one, that's called the citric acid cycle. And then the final process is called electron transport. Electron transport. And these are 4 major processes that it takes to get all this stuff right here on this screen done. This does not happen all at once. It happens little by little by little through processes that we call glycolysis, the transition step, the citric acid cycle, and electron transport. Now, for each of these things, you need to know several things about them. I am not going to have you write down individual chemical reactions, but you do need to know some things about them. For example, you need to know where each of these is happening in the cell. Is it happening in the mitochondria? Is it happening in the cytoplasm? Where? Where is glycolysis happening? Where is the transition step happening? Where is the citric acid cycle happening? For each of them, I want you to know what the starting molecules are and what the ending molecules are. You're not going to need to memorize individual chemical reactions. I'm not going to test you on them. This is going to be an open note test anyway. So you need to know what the starting molecules are the ending molecules, let's call them. What do you end up with at the end of glycolysis? What did you start with? What starts off the citric acid cycle? Right, so you're also going to need to be able to tell me how much ATP is made at each of these steps. And also, how much NADH and FADH2, that little 2 won't go in on my margin here. Whoops. Back. So you're going to need to know at least how much of this. And again, this is going to be in your notes. You take good notes, you're going to be fine on this open note test. Alrighty, so each of those things, and we will be getting to those for the next lecture. Before we get into the details of these, I do want to talk about the exam. The next exam, I don't even remember what we scheduled it for to begin with, but we are off that schedule, so you all need to be paying close attention to the new schedule. You need to be keeping up with lectures or you're going to be missing stuff. Okay, so our next exam is Thursday, April 23rd. It's going to include everything from our last exam, so includes everything in lecture, and you can review all the lectures because I'm leaving them up on YouTube, obviously, from lectures April 6th through April 21st. Okay, we are not there yet. Obviously, this is the lecture for the 14th. So there's today's lectures, there's the 16th lectures, and there's the 21st lecture that I will have all up for you, and you will have an exam for that on the 23rd. You may take it any time of day on April 23rd, but you need to take it on the 23rd. Again, this is an open note, obviously an open internet exam. This class is not designed for that sort of thing. It's not ideal. None of us like that. But we're basically asking you, did you take good notes? Do you know where to find things in your notes? Can you write and describe some of these things in your own words for me? That sort of thing. It's as long as you took good notes, you're going to be fine, and you can find them in your notes. So please make sure you're doing that. You will not be able to change your answers. Once you submit an answer, that's it. So you need to be absolutely sure. So you need to take care to make sure that you go through your notes, that you can find everything in your notes, because you need to answer one question at a time. This is like they do the GRE, for example. You don't get to go back and change and review your answers. So, and that's the compromise, because this class is not designed to have open note, open internet exams. But please, you gotta take it on the 23rd. Plan ahead. Unless you are being deployed by the military or something, you should be able to find a time, day, afternoon, night, morning, whatever time works for you, on Thursday, April the 23rd. So we will have that then. And I will be back shortly with the rest of our lecture for this week. Take care, be well, socially distance as much as you can, stay home if you can, and be well.